So since we have seen the register memory reference CPU in the previous video, now let's understand the register reference CPU. So as the name suggests, here both of our operands are in registers, right? So this is the schematic diagram. So let's understand this block diagram. This is my CPU. This is my arithmetic logic unit, and all these register references, everything is in the context of ALUs, right? I have my control unit here, other registers, everything. Here is my register file, right? Let's assume I have n registers here. So my ALU takes the inputs from two registers. Look at this. It takes one input from one register, the other input or other operand also from a register. So it takes both operands from registers, and the output is returned to another register. Look at this. The output is not registered to the inputs, to the same registers from which we are taking input. We could write to a completely different register, right? So this is how it works. Now the question here is, okay, so let's look at examples, right? So imagine I have instruction 1 which looks like this. So what does this mean? This means whatever is there in register 1 and register 2, add them up, and store the resultant in register 0. That's what this means, right? So this is my destination register. This is my source 1. This is my source 2, or this is my operand 1. This is my operand 2, and this is my destination, right? That's what this diagram also says, right? I can take one register as input, another register as input, and I can write the output to any other register. Now, if you notice here, there are three addresses. This is the address of the destination register, first operand, second operand. So these are called as three address instructions because there are three addresses. The destination, so let me write this down here for you. So this is your destination, this is your operand 1, this is your operand 2, right? And this is obviously your opcode, which tells you what is the operation that you have to perform. Very simple. Now here there is one more very important piece, which is how is data loaded into the register file itself. Data is loaded to the register file from main memory using load and store instructions. So there are special instructions called load and store instructions which are executed using the help of control unit. And when you say load something to some register, this control unit loads the data from the main memory to the register file itself. That's how the whole thing works, right? So let's look at a simple example. Look at this. Imagine I want to compute this, and let's assume A, B, C, D are memory addresses. So here, look at this. My first instruction here is load R0, A. This is the load instruction that I was talking to about here. So what this does is it loads from memory address A, whatever data is here, it loads it into register 0, right? And notice this is a two address instruction because I have an address of a register and I have address of a memory location. So this is a two address instruction, right? Now similarly, I load B into R1. Whatever is stored in memory address B, I'm storing it into R1. Cool. Now look at this. This is a three address instruction here. This is a three address instruction here. So in this three address instruction, what am I doing? Whatever is there in R0, I'm adding it to R1, and the resultant I'm storing it in R0. Here, unlike this example where these three registers are distinct, here the same register is used as destination and also for operand 1. And that's perfectly alright. That's allowed. Okay. Next, whatever is the resultant now is stored. See, what does R0 contain now? R0 contains A plus B. Right now. Right? That's what we have done. Now we are loading C into R1. So this C we are loading into R1. Then we are loading D into R2. Right? Now look at what we are doing here. We are adding R1 and R2 and storing the resultant into R1. So what does R1 contain now? R1 contains R1 and R2. R1 was loaded with C. So C plus D is in R1. Right? Now finally, here I have another three address instruction. What does it do? It says whatever is there in R0, multiply it with R1 and store the resultant in R0. So what would this result in? R0 will contain whatever is there in R0, which is A plus B. Multiply this with whatever is there in R1, C plus D. That resultant you store it back to R0. So similarly, finally, what we are using a store command here. Whatever is there in R0, store it to memory location X. Look at this. Look at how many. See, here I am only using registers R0, R1 and R2. Right? So I'm using, so this is a very nice example wherein I'm using, even though I have lots of registers, Here I'm only using 3 registers to solve this problem. I can rewrite this program slightly differently, where I might end up using more than 3 registers, right? For example, here I could say instead of R0, R1, I could say I want to use R2 also, right? So I can do all of that. So this is a very efficiently written program where I'm only using 3 registers, even though I may have more registers. It's always important to have your machine level language or assembly level language like this written with as few registers as possible, because that will be more optimal code that you can execute better. Now, there is also something called as 4 address instructions. These are not widely used nowadays, but it's good to know about it, right? So your 4 address instruction has an opcode, right, which tells you what operation you want to perform, your destination address, your operator 1, your operand 1, which we call it as source 1, your operand 2, which we call it as source 2. So till here it is the same as your 3 address. Till here it's same as your 3 address instruction. But here there is one more additional address. This is the address of the next instruction that you want to execute after executing this instruction. Let's assume this is instruction 1, right? So this gives you the actual address that you want to jump to when you're so instead of executing I2 right after I1, this could give you an address location of the next instruction. This could store the address of, let's say, I20, right? So I20 is also in memory, right? Remember, your source code or the program you're writing is also in memory. So if it stores the address, if in here I have the address of instruction I20, then what happens? First this instruction is executed, and then I jump directly to I20 without executing these instructions. Okay, so this is not widely used nowadays because most modern microprocessors use program counter, because program counter anyway has the address of the next instruction that has to be executed, right? Program counter has the address of next instruction to be executed. So in the case where I have in the case where I have my program counters, PC is a program counter, right? This is one of the very popular and very widely used registers, which is part of your control unit in your CPU, right? So again, you already have this. We discussed about program counter already, right? So because we have program counter, this is not used widely. So in most modern microprocessor, we have up to 3 address instructions, wherein we use program counter to decide what is the next instruction that we want to execute, instead of having a scheme like this. We don't use this at all, or we don't use it in most modern microprocessor. There may be some research purpose microprocessors which might use this, but to the best of my knowledge, most modern microprocessors don't use this, right? So here, since we have understood about all the CPU architectures, let's understand the instruction execution sequence. Even though I have explained this briefly to you through multiple examples, I just want to go into slightly more detail here. So imagine a world where imagine an example, right? Where we have an accumulator CPU, which means one of your operands is always in the accumulator and the resultant is always stored into the accumulator, right? We have seen the accumulator CPU, right? Just a couple of videos prior to this. Now imagine I have an accumulator CPU which has fixed length instructions. Let's assume my instruction length is 8-bit. Of this 8-bit, and let's assume all I have is 1 address instructions. Just for simplicity, okay, just so that you understand the instruction execution sequence, let's just assume that I have one address instructions only. In these 1 address instructions, I have 3 bits for opcode and let's say 5 bits for address. Okay, just for simplicity. Now, given this, how does the whole thing work? Till now, we understood about fetch and execute cycle. There are a couple of more details that we might want to get into. In the fetch cycle, what happens? Let's understand the fetch cycle, right? In the fetch cycle, the control unit, see, this is controlled by the control unit, not by the arithmetic logic unit of your CPU, right? Your CPU consists of broadly ALU and control unit and a bunch of registers. Some of them controlled by the control unit. Like for example, your program counter is heavily influenced by your control unit, right? Your general purpose registers and accumulator type of registers are all used by your ALU more widely. Okay, so in the fetch cycle, what happens? The program counter, the CPU, specifically not just the CPU, specifically the control unit in the CPU reads the program counter. Program counter anyway points to the next instruction that we have to fetch and execute, right? So the CPU uses the data in the program counter. By CPU, I specifically mean the control unit of the CPU. The control unit of the CPU generates the memory request, because control unit does all non-arithmetic logical operations as part of the control unit, right? So the control unit generates a memory request. This memory request is sent to the memory. So there is a read request. So we set read equals to 0, right? We also place the address, right? Again, what is this address? This is not this address. This is the address of the next instruction that we want to fetch. Right now we are still in the fetch cycle. Don't forget that. Okay. So this is the address of the next instruction, which is stored in your program counter. We send it to the main memory. The main memory will return the instruction. Okay. Let's assume my main memory is 1 word equals to 1 byte. So let's assume my main memory is 1 word equals to 1 byte, which means 8 bits. Okay. So these 8 bits that the memory transfers back to the CPU, we store it in a special purpose register called as instruction register, often referred to as IR. Instruction register stores the current instruction that is being decoded and executed, right? So I've already fetched the instruction register, right? See, look at this. Now my PC will be updated because I've already fetched from the memory the next instruction and stored it into instruction register. My PC gets updated and it points to the next instruction that has to be executed. Now the instruction register itself is broken up into 2 parts. The first part for the opcode, the second part, the last 5 bits for the address. Now here internally what happens is, because this accumulator based microprocessor or accumulator CPU already has a fixed length instruction, it knows that the first 3 bits are opcode, and there are only 1 address instructions in this case. So it creates a decoder. So these 3 bits that are there are passed through a decoder. This decoder is 3 cross 8. Why is it 8? Because 2 power 3 is 8. This is a 3 cross 8 decoder, right? So there are 3 bits input and 8 bits output. Now these 8 bits, each of these will correspond to one operation. For example, you could have something like this. You could have 0, 0, 0. So if the 3 bits here are 0, 0, 0, which means my opcode is 0, 0, 0, it could correspond to add operation. If it is 0, 0, 1, it could correspond to multiplication operation. If it is 0, 1, 0, it could correspond to subtract operation. If it is 0, 1, 1, it could correspond to the load operation, right? There are multiple operations that are possible. There are multiple instructions that are possible, right? So now this whole thing, what binary encoding corresponds to, so which binary encoding corresponds to which operation, either a load operation or an arithmetic or logical operation. This is sometimes stored within a ROM. A ROM is a read-only memory. You can't write it. It's like fixed memory. Okay, sometimes it is written in a ROM, and this whole logic, so this is called as design time binding. This whole thing is called as design time binding. Why is it called design time binding? Because when the person who was designing the accumulator CPU, the person who was designing this CPU, at the design time itself, he or she decides that 3 zeros corresponds to add, 001 corresponds to multiply operation, 011 corresponds to load. So this mapping from the 3 bits to the actual operation that has to be performed is decided at the design time. That's why it's called design time binding. This is called binding because what corresponds to what? This is decided at the design time itself by the person who is designing this CPU. And sometimes this information could be stored in a read-only memory. Now this whole information on what operation we have to perform is sent back to your control unit. Right? The control unit now decides how to execute this. So this stage is called instruction decoding. Because what are we doing here? My instruction is a 3-bit opcode. Okay, because my opcode is 3 bits. I'm taking these 3 bits, I'm decoding them to understand what operation we have to perform. Is it an arithmetic logical operation, or is it a memory read operation or a memory write operation? What operation we have to perform? That decoding is happening in this stage. And then the control unit takes over. The control unit also has a special register called PSW. This is also sometimes referred to as a flag register. It's called the program status word. Okay. So what happens is program status word stores all the miscellaneous information. about the currently executing instruction. Look at this. The currently executing instruction itself is stored in instruction register. But some metadata, some information about the... So for example, right now, let's assume we are performing an add operation. Okay, some information that we need to store temporarily while this instruction is being executed is stored in PSW, also called as flag registers. Again, we'll study about PSWs, what type of information is stored, how PSW itself is organized in one of the next videos. Okay, PSW is a very nice topic that we'll learn of little later. Okay, so just let's keep that aside. But control unit also has access to this type of register called PSW, in which it stores all the miscellaneous information temporarily while the instruction is being executed. The instruction itself is stored in the instruction register, right? Now the third phase is called as a operand fetch. In the operand fetch stage, now the control unit knows, for example, the control unit knows that it's an add operation. Okay, and because my opcode corresponds to add, and I have some address. Now it has to obtain this, whatever data is stored in this address, it has to obtain it, right? That's why it's called the operand fetch. Because in accumulator CPUs, the first operand is anyway there in accumulator by default. The second operand could be in a register or it could be in memory. So we need to fetch this from the register or memory to the temporary register of the ALU, right? So for example, imagine this operand is in a register. Then the control unit sends the register address to the register file. The register file, suppose this register address corresponds to this register. This register value is sent to ALU and it is stored temporarily in the temporary register of the ALU itself. Right? On the other hand, if the operand is in memory, then the control unit sends the memory address to the main memory. The main memory sends us the actual data that is stored in this memory address to the ALU, or to be more specific, to the temporary register in the ALU. Now what does the ALU do? The next stage is called the execute stage. In the execute stage, my ALU will take one input from the accumulator, the other input from the temporary register. Remember, in the previous stage, my temporary register, because my data from the register or from memory is stored in the temporary register. So it takes these two inputs, it outputs it back to the accumulator. Again, this is the instruction execution sequence of an accumulator CPU. If the CPU architecture is different, the logic will be slightly different, but the broad stages will be the same. You will have a fetch cycle, you will have a decode cycle, you will have an operand fetch cycle, then you will have an execute cycle. One very important thing here as far as the execute cycle is concerned here is, look at this, my control unit knows that this is an add operation, right? And we have to fetch the operand. The control unit is what is orchestrating all of them. The control unit takes the data from the program counter, right? From the program counter and gets and loads the data into IR. It's the control unit which actually takes the data from the decoder and understands that what we have to perform is an arithmetic operation. If it's an arithmetic operation and we have to fetch an operand, it will fetch the operand, then it will give control to the ALU. It is the control unit which tells the ALU to take the input from the accumulator and the temporary register and execute the actual operation itself, right? So the control unit, very importantly, the control unit is the master orchestrator. Like in a musical theater show, it is what is controlling all of these stages one by one, very, very carefully, right? So it's a very ingenious way. Again, we have discussed about this in the previous videos also, but I just wanted to write these stages clearly as a fetch cycle or a fetch stage, instruction decode stage, operand fetch stage, and execute stage. And the control unit is the master controller which is orchestrating this whole execution of the whole instruction itself. This sequence itself is controlled by the control unit, right?